Today we're going to be asking the question, what happens if we take the limit of a sequence? And before we do that, let's remind ourselves of a few limit properties from Calc 1. For the purpose of this unit with sequences, we're only going to be looking at what happens as our values approach infinity. So I'm only going to remind you of what happens in that case. So in Calc 1, we saw some rational functions where x approached infinity. That would be these first two examples. Remember, rational functions are a polynomial over a polynomial. If we have a rational function and x is approaching infinity, things behave really nice. We just look at the highest power of x in the numerator and denominator and get rid of everything else. The reason we do that is because x is getting really big, and so only the highest power will, highest power will contribute the most. Everything else will be negligible in comparison to that highest power. So in this first case, we're gonna have 3x squared over 5x squared. We simplify that to 3/5. As x approaches infinity, 3/5 is just 3/5. So this first limit will just be 3/5. This next one, we have 6x over x cubed. When we simplify that, we're going to get 6 over x squared. Now, as x approaches infinity, we're going to get 6 over a very big number. And 6 over a really big number is something really small, something really close to 0. So this will be 0. Okay, so that works great for rational functions. A polynomial divided by a polynomial, just take the highest power in the numerator and denominator. This next example is not a rational function because natural log is not a polynomial. So we can't use that method. But in this case, we notice that if we plug infinity in, we get infinity over infinity. And so what we're going to do here is we're going to use L'Hopital's rule. So we remember that L'Hopital's rule can only be used if we get infinity over infinity or 0 over 0. For our purposes, we're really always going to be in the infinity over infinity case. So if we get infinity over infinity, we can use L'Hopital's rule. And we remember that L'Hopital's rule tells us that we can replace this limit with the derivative of the numerator and the derivative of the denominator. We're not doing a quotient rule in L'Hopital's rule. We're just looking at the numerator and denominator separately. And let's go ahead and simplify this. So this will give us, if I multiply the numerator and denominator by x, this will cancel out. We'll get 3x cubed. As x approaches infinity, this is going to be 3 times a really big number, which is going to be infinite. So we're going to get infinity out here. So hopefully that's a good review of what we did in Calc 1. So we've got our rational functions and we've got L'Hopital's rule. Those are really kind of the two big things that we'll use here. So here what we want to do is we want to talk about the limit of a sequence, and let's think about what does that mean. And maybe I'm going to look at this second example here and try and explain what this means in regards to the second example, and then we'll go back. So the second example, we have the sequence 2 over n. So let's write out a few of the terms. So we've got, if I plug in n equals 1, I have 2. If I plug in n equals 2, I have 1. If I plug in n equals 3, I have 2/3. Then we have 2/4 and 2/5, and we can keep going. So let me think about graphically what this would look like. So what I'm going to do is I'm going to graph n on the x-axis and a sub n on the y-axis. And so when I plugged in n equals 1, I got 2 out. When I plugged in n equals 2, I got 1. Then I got 2/3. Then I got 2/4, and then I got 2/5. These numbers are getting closer and closer to 0. We notice that this is a distinct set of points. This is not a curve. I'm not going to connect these dots because we're only plugging in natural numbers. We're not plugging in like a half into our n values. But we do notice that as n gets bigger, these values are getting closer and closer to 0. The fact that these values are getting closer and closer to 0 is going to make us say that the limit of the sequence is 0. So in this case, we'll say the limit as n approaches infinity of a sub n is 0. And so if we go back and look at this definition that I have in the box up here, what it means to say that this limit is 0 means that we can make the values of the sequence as close to 0 as we want, and if we take a big enough n value. So if we pick bigger and bigger n values, these terms are getting closer and closer to 0. In the event that we're in something like this, where we're getting a number out from our limit, we say that the sequence converges. We say that this particular sequence converges to 0. So in this case, we would say this is a convergent sequence, and it converges to 0. If the sequence, if that limit does not exist or is infinity, then we say that that sequence diverges. So converging means that we're getting closer and closer to a single value. Okay. The way that we really take limits instead of just looking at graphs here is we can take limits exactly like we did in Calc 1, exactly like we did in those first three examples. So for this example, with 2 over n, we could look at the limit as n approaches infinity, 2 over n. Now we're just using n instead of x, doesn't really matter. So in this case, we're going to get 2 over a big number, which is 0, and that agrees with what we got. So since we got 0 out, we say that the sequence converges to 0. Okay, so maybe you should try those other three before you watch me do them, but I'll go ahead and do them. So in this case, we can look at the limit as n approaches infinity. This is always how we're going to start. We're going to start with the limit as n approaches infinity of one of our terms. Okay, now we have to use Calc 1 techniques to find that limit. This is a polynomial over a polynomial, so we take the highest power, which is n over n. N over n simplifies to 1, so we're getting 1 out from this limit. We got a concrete number out, so this sequence converges. So the sequence converges to 1. That means that the values, the individual terms of the sequence are getting closer and closer to the number 1. Okay, keep working. So we can look at the limit as n approaches infinity, e to the n over 2. This is not a polynomial over a polynomial. If I plug infinity in here, we're going to get infinity over 2. That's not a L'Hopital's case because it's not infinity over infinity, but over infinity over 2 is just a big number. Sorry, I got something in my eye. So we're getting infinity out here. This is not a number. So this means that this sequence diverges. It is not convergent. So this is a divergent sequence. Divergent sequences just mean that the values, that the terms of the sequence are not getting closer to a particular value. In this case, the terms would be getting bigger and bigger. They're getting more and more infinite. But sometimes we could have a sequence that bounces back and forth. Maybe it does something like this. It kind of bounces all over the place. That would be divergent as well. So we don't have to be getting things that go to infinity in order to get a divergent sequence. Okay, and now if we look at this last one, we can look at the limit as n approaches infinity, n squared over e to the n. Again, because of that e to the n, this is not a rational function. So we have to go ahead and plug infinity in. We're going to get infinity over infinity, which tells us we can use L'Hopital's rule. So for L'Hopital's rule, we're going to replace the numerator with the derivative of n squared, which is 2n, the denominator with the derivative of e to the n, which is e to the n. Now we plug infinity in, we get infinity over infinity again, which means we need L'Hopital's rule again. If you remember from Calc 1, we can use L'Hopital's rule multiple times if we want. So now we're going to get 2 over e to the n. Finally. So now we're going to get 2 over infinity. That's 2 over a big number, which was going to give us 0. So this last sequence converges to 0. This is a convergent sequence. So the values, the terms of the sequence get closer and closer to 0 as n gets closer to infinity.